Okay, so let's pick up part two. We're going to talk about some really cool stuff here. We're going to talk about isomers. Now, you've probably heard of isomers. Isomers basically mean different molecule made out of the same atoms. So it may look a little bit like each other. They may not look like each other, but they have the same constituents in them. And we'll find there's a lot of different kinds of isomers. One is basically they have the same molecular formula, as I mentioned, but they're in a different structure and they'll have different properties. So here we have butane, just regular N-butane in a straight line. And then here we have isobutane, which has instead a methyl substituent. This would actually be methylpropane, also called isobutane, because it's an isomer of butane. Now the connectivity of the carbons is different because each of these carbons in N-butane is only attached to two other carbons, with the exceptions of the ones in the middle. Now, this carbon in the middle of isobutane is attached to 1, 2, 3 carbons, so it's different. It's a different way to arrange those molecules. So the name is different and the chemical properties are also different. You'll find that butane and isobutane will have different boiling points and different melting points than each other. Butane will have a slightly higher boiling point because it's a longer molecule and can form more London dispersion forces than isobutane can, because isobutane is more compact. It's not as long, and so it can't make as many of those London dispersion forces. So it will be slightly different properties. Now, we can also have structural isomers like I showed you before, and we can have conformational isomers. Conformation meaning shape. Now, we look at these two. Now again, this is the butane example we had before. They are structural isomers because the carbons are different. This carbon is attached to 2 carbons, and this carbon is attached to 2 carbons. But this one's attached to 3. That makes it structurally different. It's a structural isomer. Now, that is not the same for a conformational isomer. That just has a different shape, but it's the same molecule still. And this was an example I gave you, because I'm a mean person, on your last workshop. You'll notice 4 carbons in a row, 4 carbons in a row. They just go, instead of all the way across, we just draw one going up. And so if we were to give the skeletal structure, this would just be the normal skeletal structure, and this would, instead of going down, 1 up, down, it goes up instead. These aren't different compounds. They're exactly the same. They're just drawn in a different way. So we call these conformational isomers, because these are single bonds. They can move around, they can take up different shapes, but all the carbons and all of the hydrogens are attached to each other in exactly the same way. So even though they're different shapes, they're exactly the same molecule. So we call those conformational isomers, meaning only the conformation, only the shape is different. And those shapes can change constantly. Now, this is something you've probably heard about. Different isomers being cis and trans isomers. What does that mean? Well, when you have a double bond, you can't freely rotate a double bond like you can a single bond. And you think about it like this. If I put my 2 fingers together like this, I can freely rotate them and keep my fingers touching. So if this was a chemical bond, I could maintain that chemical bond while freely rotating around it. But if I have a double bond, now I'm stuck. I am stuck in this position. I can't freely rotate. So notice my thumbs are now in different positions. One is up and the other one is down, and I can't rotate without breaking the bond. I can't rotate without breaking this bond or breaking that bond. So if I have two bonds, they're stuck in space. And so if my two substituents, like my thumbs I was showing you, are on the same side of the bond, we say they're in cis. So this one, this methyl group, and that methyl group are on the same side. They're on the top of the double bond. So we say that they're in cis. If they're on opposite sides, like my thumbs are in this position, they're in trans. One's on the bottom and one's on the top. So we say that that's trans 2-butene. So we have to, not only do we have to say that it's 2-butene, there's two different ways to draw that. One where we have the methyl groups on the same side, and one we have the methyl groups on the opposite side. So that's double bonds that can't rotate. Now we don't have this rule with triple bonds because there are no substituents on a triple bond, right? Double bonds, we have substituents. So single bonds can freely rotate. Double bonds cannot. Double bonds, you are locked. And if you were making models in the lab, you would see that once you connect something with a single piece, you can move them around. You put two pieces and they're locked. So same side cis, opposite side trans. So here we don't have double bonds, but we have a ring. And the same thing happens in rings, because rings basically, because it's all connected together, you basically can't, you can move a little bit, you can have a little bit of movement in the ring, but it's not as much. So you can bend it a little bit, but because they're all joined together, you can't completely flip these bonds. So here we have cyclopropane. So only 3 carbons, one here, one there, and one there. And so in this, we also have cis and trans, because we would have to break bonds in order to put them on the same side. So imagine this as basically a ring, and we have above the ring and below the ring. So when they're in cis, they're on the same side of the ring. They're above it. And in trans, they're on opposite sides. One's above the ring and the other one's below it. And again, because it's a ring, you have some bending, but you can't break it completely. And so those methyl groups will stay either on the same, either on one side of the ring or opposite sides of the ring. And this is really important when we get to organic and bioorganic, biochemistry. Isomers are super important because they can have vastly different properties. So here is a molecule called carvone, and you find it in spearmint, gives it that special smell in spearmint, and you also find it in caraway seeds, where it has a different odor. Now these two things are isomers of each other, and this is a very special class of isomers. We call those stereoisomers. And we introduce the idea of chirality. Chirality is when you have a carbon that has 4 unique substituents on it. They're different. And on one molecule, they'll be in different locations than on the other molecule. You'll have exactly the same atoms, you'll have exactly the same number of atoms, but they will be arranged in a slightly different shape. And I'll get to why they're called stereoisomers in a minute. But these have different shapes. You'll see one has groups coming out of the ring, and another has groups going behind it. And just that is enough to give it a different shape and for your body to be able to tell the difference between one or another. I don't think anyone's going to be able not to tell the difference between spearmint gum and caraway seed gum. They're going to taste different. So let's get into what chirality means. Now, these are molecules that you can't superimpose on top of each other. Stereoisomer is a chiral molecule. I sort of mentioned a chiral molecule has a chiral carbon in it that has 4 different substituents. So they're in the same area. They have the same molecules and the same atoms in the same place, but they're arranged differently. And you can't superimpose them on another. I like to say that they have handedness, because your left hand and your right hand both have 4 fingers and a thumb, and they're put together in the same way. You know, your thumb's on top, and the second, your pointing finger and your middle finger and ring finger and pinky, all in the same location. But you can't put one hand on top of the other one, because my thumbs are in different places. They are mirror images of each other. So if I put my left hand or my right hand in a mirror, it would look like my left hand, right? I can sort of put them on top of each other like this, but notice that it's because my palms are together. Or I can put them together and they look the same when I put the backs of my hands together. But I cannot put the backs back to back. They are different now. And so these would be isomers. They'd be stereoisomers of each other. They're mirror images. And so mirror images are different. Chemically, biologically, really important that they're different. And so you can't superimpose them on top of one another. And we have a special name for those molecules. We call them enantiomers. They are non-superimposable. They are mirror images of each other. One is flipped one way, one is flipped the other way. And we can't put them on top of each other and have them be the same shape. If we can do that, then they're identical. But we can't do that in this instance. So as you can see, with carvone, one of them has this group behind the ring, and the other has this group in front of it. And so you can't stack them on top of each other, because one will be up and the other one will be down. And if you flip them the other way, the other one will be up and the other one will be down. So they're mirror images of each other. They're enantiomers, meaning they have put together exactly the same way, but in a different order around one of the carbons. So like another example is a pair of shoes, you know, your left shoe and your right shoe. You can put the soles together and they match, but you can't put them on top of one another because one bends one way, the other sort of bends slightly the other way. So we call these things chiral, and like most things in chemistry, they either come from Greek or Latin. This is one from Latin, meaning hand. So like I said, they have handedness. And so most enantiomers have a chiral center. That is a carbon, a tetrahedral carbon, so it's attached to 4 different things, and it has 4 different atoms or groups of atoms. So in this instance, we have methane that's attached to a hydroxyl group, a hydrogen, a methyl group, and an ethyl group. Excuse me. So those are 4 different groups. Now, if this was planar, we could just stack one on top of the other and they would be the same. But these are tetrahedral. They don't stack on top of one another because however you try and stack them on top of one another, 2 of those things are going to be in different places. So those are chiral. Those are chiral molecules because of the tetrahedral shape. Like I said, if it was planar, you could figure out some way to stack them on top of one another. But when it's a tetrahedral shape, they're going to be in different locations. So how do you identify which carbon, or if any of the carbons in a molecule is chiral? Well, first you find the carbons, and remember they have to be singly bonded. There has to be 4 different things attached to the carbon. Well, here's my carbons that are all attached to 4 atoms. So there's one, there's one, there's one, there's one, there's one, there's one. None of them are double bonded, none of them are triple bonded, none of them are in a ring. So, okay, they're all tetrahedral. What's next? Look at each one and see if the 4 groups attached to that carbon are the same or are they different. Well, this one has 3 hydrogens attached to it, so that can't be it. This one has 2 hydrogens attached to it, that can't be it. That can't be it, and that can't be it. So it's either this one or this one. So we look a little closer and we see that this carbon has a methyl group attached and another methyl group attached. So it has 2 of the same things. So that can't be it. Leaving this carbon. So that particular carbon has an ethyl group on one side. It has a propyl, an isopropyl group on another side. It has a bromine and it has a hydrogen. It's got 4 different things attached to that carbon. That carbon is chiral, meaning we could arrange a different order of the exact same substituents on that carbon and it would be different. What does that mean? Well, these molecules are also known as being optically active. That means we can tell these things apart just by shining a light on them. And how we do that, we take a solution of something like that and we shine a polarized light in it, meaning light sort of that's going up and down in a single direction. That's what a polarized light is. Just white light from the sun is coming at you in all directions. We put that through what's called a polarizer, and we have light that's just going, all the waves are the same, going in one direction. We shine it at something like that, and if there's chiral molecule in it, it actually bends the light, it rotates it in one direction or the other. It either turns it clockwise or counterclockwise. And that's how we can tell which form of the molecule it is. If it turns it counterclockwise, we say it's one version. If it turns it clockwise, we say it's the other version. If it's an equal mixture of both, then it doesn't rotate it at all. And we call that a racemic mixture. A racemic mixture has equal amounts, has a 50-50 mix of each chiral molecule, and so you can't tell them apart because one will bend the light one direction and the other one will just bend it right back. So basically you get nothing. We call that a racemic mixture with a 50-50 mix of both stereoisomers. Now here are some of the consequences of chirality. We already mentioned caraway seeds and spearmint. This one I find even more bizarre for some reason. You find the same molecule in the skins of lemons and oranges. They're both called limonene. One of them has this particular shape. The other one has this particular shape. And they're not identical. You can't place them on top of one another. So this one has a double bond on the ring on one side. This one has a double bond on the ring on the other side. And you can't stack them together because this part is coming up. If it was flat, you could stack them on top of one another. But we can't stack them on top of one another because this group is coming out in 3 dimensions, coming out at us. So they are enantiomers. They're stereo images. They're mirror images of each other. And we say one is R for being right-handed, and we say the other one is S for being left-handed. S stands for sinister because people didn't trust left-handed. Don't trust lefties. They're sinister. And just that difference leads to them having distinct odors. One smells like a lemon and the other smells like an orange. And you can tell the difference. And it's because our smell receptors respond to the shape of the molecule. It's not just the molecule itself, but what shape is it? If it fits perfectly into the receptor gives a response. If it doesn't, you get a slightly different response or you get no response at all. And so one of us gives the response for oranges and the other gives the response for lemons. A more important, sad story about chirality. You may have heard about thalidomide. This was a drug given in the 50s to treat pregnant women who were having morning sickness. And so a pharmaceutical company made this particular molecule, and it indeed did alleviate morning sickness. The problem was that it's a chiral molecule, and only one of the stereoisomers was used to treat morning sickness. That one was. The other stereoisomer caused birth defects. It's what we call a teratogen. It gets intercalated into DNA and causes mutations and birth defects. The only difference is a single carbon, where the arrangement of the groups on that one carbon changes everything. And the problem was this was synthesized in a solution that got a 50-50 mixture of both. And that will happen when synthetic chemists are just synthesizing a molecule in the lab. Generally, you're going to get both versions of it. So it was originally sold as a racemic mixture. It was a 50-50 mixture, unfortunately. And so it did both. It did a good job of treating morning sickness, but it also caused birth defects. And you may have seen a lot of this in Japan and in America, where these sort of babies were born without arms, like so-called flippers, and it was because of thalidomide. So you got these really severe birth defects. Now, if that company was able to just synthesize one of the enantiomers, it would have been fine. You would have been able to treat morning sickness, and it wouldn't have caused birth defects. And that leads to this year's Nobel Prize in Chemistry. It was given to two chemists, one of whom actually worked as a postdoc, where I was a postdoc in San Diego. It's at Scripps. And they developed independently using small organic molecules as catalysts instead of metals, which a lot of synthetic chemists use metals as as catalysts because metals, they dissolve gases on them. They, have certain bonding regions that are important for getting molecules in the right place. But they're not chiral, they're not carbon. So you make both enantiomers when you start with a metal catalyst. Now, what these two chemists realized was that if you started with a small organic molecule, and like a really small organic molecule, like an amino acid, for instance, all the amino acids that goes into our proteins, they are all a particular stereoisomer. They're either R or they're S. You don't have both. And so they are already chiral. So they noted that if you started with a chiral molecule as a catalyst, the molecule you then made was chiral, but only one of the enantiomers would be made. So you could specifically arrange in three-dimensional space which enantiomer you wanted to make, depending on what was the structure of your original starting material. So it was a genius idea. People have been using much larger molecules for doing chemistry, for doing synthetic chemistry. They had the genius idea of why not just use a very, very, very simple molecule that you can just pull off of a shelf, and they won the Nobel Prize in chemistry for it. So tells you a little bit about how important chirality is. We'll talk more about this on Tuesday. All right. Hopefully when it stops raining. All right. Bye-bye.